In section 5.2, we'll explore one-to-one functions and inverse functions. We'll discuss why one-to-one functions are necessary for inverse functions and how to find the inverse of a function. Precalculus Online starts right now. Let's take a look at section 5.2, one-to-one functions and inverse functions. So let's start with one-to-one functions, and here's the definition. A function, Fn is an abbreviation for a function, is one-to-one, and 1-1 is an abbreviation for one-to-one. So a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. So in math symbols, that means if x1 is not equal to x2, so that's the two different inputs, then the conclusion must occur, and that is two different outputs. Well, the outputs are, let's say, f of x1 and f of x2, and these must be different, so we say that they are not equal. This is a little confusing. We have not equal and then more not equal and stuff like that. So something that we can do to sort of clarify this is to rewrite this as the contrapositive. Contrapositive is when you take an if-then statement and you flip around the conclusion and the hypothesis and negate them at the same time. So we end up with if f of x1 is equal to f of x2, then it must be the case that x1 is equal to x2. And this is usually the way that we go about showing that a function is one-to-one. It sort of works out better. But now let's think about what this contrapositive says. It says that if I have the same y value on a graph, then the only way that that could have happened is if I had used the same x value to derive that y value. In other words, no two different x values could possibly create the same y value on a graph. Let's show an example of this. Number one, determine if the following functions are one-to-one. So one thing that you can do here is you can just scope this out, and you can see, for example, right here, I guess. If I draw this horizontal line, I end up with these two different points that have the same y value. So I've met the first part. The y values are the same, but then these x values, here's x1, let's say, and here's x2, and those two are definitely not the same. So this function is not one-to-one. In the second part here, though, go ahead and try this. Sweep your pencil up from the bottom horizontally over this function. And you'll see that you can do that without intersecting the graph more than once. If you can sweep your pencil horizontally from the bottom through to the top without intersecting the graph more than once, then it is one-to-one. And that is called the horizontal line test. And we say that the graph passes the horizontal line test, and therefore it is one-to-one. Let's take a look at proving that a function is one-to-one. So here are the 3 steps to proving that it is one-to-one. First, set f of a equal to f of b. and simplify that. Then try to solve for a. If you get that the a must be equal to the b, and that's the only choice, then f is a one-to-one function. But if you get that a could be equal to b and the a could be equal to something else, then that proves that your function is not one-to-one. So let's take a look. Example number 2. Prove that f of x equal to 7x cubed minus 9 over 2 is a one-to-one function. So first, let's take f of a is equal to f of b. Now this simply means plug in a for the x's on the left side and plug in b for the x's on the right side. So we get 7a cubed minus 9 over 2 is equal to 7b cubed minus 9 over 2. Now we want to try to solve for a. We'll try to solve for it on the left side. So the first thing I'm going to do is I'm going to multiply both sides by 2. When I multiply both sides by 2, the 2's in the denominator cancel, and that leaves me with 7a squared cubed minus 9 is equal to 7b cubed minus 9. Next, I'm going to add 9 to both sides. That essentially cancels the 9's. So I get 7a cubed is equal to 7b cubed. Next, divide both sides by 7. So I get a cubed is equal to b cubed. And then if you take the cube root of both sides, the cube root of a cubed is a, and the cube root of b cubed is b. Since a is equal to b, we conclude that f is one-to-one. Let's look at example number 3. Prove that f of x equal to 1/5 times 3x minus 7 squared plus 6 is not one-to-one. So we start in the same way. F of a is equal to f of b. And we plug in a. So we get 1/5 times 3a minus 7 squared plus 6 is equal to 1/5 times 3b minus 7 squared plus 6. The first thing I want to do is subtract 6 from both sides, and that cancels those. And that leaves me with 1/5 times 3a minus 7 squared is equal to 1/5 times 3b minus 7 squared. Now we're going to multiply both sides by 5. And the 5's cancel. So we get 3a minus 7 squared is equal to 3b minus 7 squared. And this is where it falls apart. Now we want to take the square root of both sides. But what is the square root of something squared? It's actually the absolute value of the inside. It's not just the inside. And that's because if you take something squared and then take the square root, you sort of lose track of what the original something was. For example, if you square -5, you get 25, and then if you take the square root of 25, you think, well, it must have been 5. But doing this with variables, you can't quite just assume that it was the positive and just leave it alone. You have to ensure that you have the positive, so that's why the absolute values come in here. Well, that's the problem. So now, in order to solve an absolute value equation, you split it up. You say 3a minus 7 is equal to 3b minus 7, or 3a minus 7 is equal to the negative of 3b minus 7. This is the acknowledgement that what you squared originally could have been positive or negative, and you don't know. If I solve the one on the left side here, I can add 7 to both sides and get 3a is equal to 3b. Divide both sides by 3, and we get a is equal to b. That's fantastic. We knew that was going to happen. On the right side, however, we're not so lucky. Distribute the negative, and we get negative 3b plus 7. And now if I try to solve for a, I get 3a is equal to negative 3b plus 14. They don't cancel. And then divide by 3, and you get negative 3b plus 14 over 3. And that's not exactly equal to b. And therefore, because you got something else, we know that f is not 1-to-1. Let's take a look at inverse functions. Here's the definition. Suppose that f is a 1-to-1 function. Then, corresponding to each x in the domain of f, there is exactly one y in the range, because f is a function. And corresponding to each y in the range of f, there is exactly one x in the domain, because f is 1-to-1. The correspondence from the range of f back to the domain of f is called the inverse function of f. The symbol, which is f raised to a little -1 power, is used to denote the inverse function of f. So a little bit note on the notation here. The -1 is notation. It is not an exponent. We're not taking the reciprocal of f. We're taking the inverse of f. So just be wary of that. Now, why have we studied 1-to-1? Well, this is it right here. This is the big moment. We need f to be 1-to-1 because of the following. If I have a function, and I have the domain of f right here, it's this little set here, and then I map it over to this other little set that's the range of f, that works out perfectly right there. And we end up with f of x, because that was the function f. But now I want to do the inverse. The inverse is the function that's going to go from the range back over to the original domain. But in order for it to be an inverse, it has to be an inverse function. So I can't have two different original x's that would be potential answers for the function if I go from right to left. For example, I couldn't start over here with the x, go over here to the range, and then have maybe one and then two different x's that are the function answers for going from right to left. That is a no-no. And that's why we need 1-to-1. It ensures that when we find the inverse function, it actually is a function. And so now the domain of f, the range of f becomes the domain of f inverse, and the domain of f becomes the range of f inverse. So when you take the inverse function, you switch the domain and the range from the original function. Let's see that in action here. Example 4. The function f gives the capital of each listed state. what is the domain of f? What is the range of f? Is this function one-to-one? If so, what's the inverse? What's that domain, and what's that range? Well, let's go after this step by step. First, we want the domain of f, and I'll use some abbreviations here. So we see how the arrows are going here. This represents f as it is. So the domain is the list of these states. So we have Texas, Oklahoma, Arizona, New Mexico, and California. And then what is the range of f? Well, the range is the capital cities. So the range of f would be Austin, do some abbreviations here as well, Oklahoma City, Phoenix, Santa Fe, and Sacramento. And then, is this function one-to-one? And the answer is yes, f is one-to-one. We know that because for any same value in the range, there was only one same value in the x's. In other words, Austin is not the capital city of Texas and Iowa, for example. Austin is the capital of Texas only, period. So it's one-to-one. Now the question is, what is f inverse? Well, to get f inverse, we just sort of switch the roles. So we're going to have Austin, Oklahoma City, Phoenix, Santa Fe, and Sacramento. That's the domain of f inverse. The range is going to be the states: Texas, Oklahoma, Arizona, New Mexico, and California. And the mapping is just straight over. Now, the mapping doesn't have to be straight over. They could be crossed and everything. But I listed them all in order. It makes it look pretty. So this is the domain. This is the range. Let's look at example 5, a similar example. The function f gives the student name for each student ID listed. What is the domain of f? What's the range of f? Is it one-to-one? If so, what's the inverse? What's the domain of the inverse, and what's the range of the inverse? So let's do the domain of f, and that would be A00001, A00023, A0000025, A0000032, and then A0000038. Then what is the range of f? Well, the range of f is Bob, Carl, another Carl. Since it's another Carl Smith, and there's already a Carl Smith I've written down, I don't have to write the second Carl Smith. Because it's a set, you only have to write these things down once. Then Dom and Eli. And then, is the function one-to-one? And the answer is no. F is not one-to-one. And it's because of Carl right here. Carl has the same name, but it came from two different domain values. It came from the domain value of A23 and A25. And that's the problem. So since this is the domain and this is the range, what we would want to do with f inverse is to make the names the domain and the student ID numbers the range. And we would want it to go from right to left. But then there's the problem. You would say, okay, what is the ID of a student whose name is Carl Smith? And that has two different answers. Well, if it's a function, it can only have one answer. And that's why this function does not have an inverse. When a function does not have an inverse, we say it is not invertible. And that's the end of that problem, because you can't go on to find the domain and the range of an inverse because the inverse doesn't exist. Let's look at the inverse function's relationship to composition. So let me start with the set bubbles again here. So we have this set bubble with x, and we're going to map it over here with f to create f of x. Now the inverse has to start with f of x and map it directly back to x. But if it does that, and I think about it in terms of f of x, I'm really mapping this to f inverse of f of x. And that has to be equal to the x itself. So from that we get the following relationship. F inverse of f of x has to be exactly equal to x for all x in the domain of f. And you can play the similar game by starting on the right side, going to the left, and going back to the right, and get the reverse relationship. F inverse of x has to be equal to x for all x in the domain of f inverse. Now, if you're worried about which domain has to be satisfied for each of these, just look right here. Whatever this first one is the one that has to have the domain satisfied. So in the first one, since you're taking f inverse of f of x, so it's the f that's used first, then that means the f has to be where the domain elements are. Same thing for the bottom. Now, problems like this will say verify. Students sometimes make the mistake of trying to start with one and show that the other one is the inverse. That's not what this question is asking for. Verify is very specific. It means to show that the compositions work out. So, verify the inverse of f of x equal to 2x plus 5 is equal to x minus 5 over 2. So you have to do both, because it is possible for one of the two compositions to work and the other not to work out. And they would not be inverses in that case. So we have to do both. So f inverse of f of x, we want that to be equal to x. So that's what we got to work toward as our goal. So f inverse of f of x is equal to f inverse of 2x plus 5, which is equal to 2x plus 5 minus 5, all divided by 2. The 5's on the top simplify, and we get 2x over 2. 2's cancel, and we get x. Check. Similarly, let's do f of f inverse of x. F inverse is x minus 5 over 2. And now I'm going to take x minus 5 over 2 and plug it into the f function. So this is going to be 2 times x minus 5 over 2 plus 5. The 2's cancel. That leaves me with x minus 5 plus 5. And then the 5's cancel, and that leaves me with x. So since I got x for both compositions, that means that these are, in fact, inverses. Next, let's take a look at the inverse function's relationship to graphs. Example 7 says, the graph of a function and several of its points are given. Draw the inverse function. So, in order to draw the inverse, we need to know this little realization, really. For a point labeled xy on f, the point y comma x is on the graph of f inverse. So in other words, if you know one of the points on F and you call it xy, you can find a point on the inverse graph by switching the x and y coordinates around. So here is a point right here that is -4, -1. So that means there's a point that's at -1, -4. Similarly, let's see, we have -2, 3. So that means there's a point at 3, -2. Here's the y-intercept of 4, so that means we have an x-intercept on the inverse at 4. And our last point here is 3, 6. So that gives us 6, 3. And then if I connect these points, like so, that gives us the inverse graph for this function. So what is sort of the ultimate relationship here? Well, it turns out that a function and its inverse can be graphed as reflections over the line y equals x. So whenever you have a function and its inverse, we say that they are symmetric over the line y equals x. And reflection over the line y equals x is the same thing as flipping the x and y coordinates around. Let's take a look at example 8. The function f of x is equal to 3x minus 1 over x plus 4 for x not equal to -4 is a one-to-one function. Find its inverse. So in order to find an inverse, you have to know that you have a one-to-one function first. If you don't, then you can't find the inverse. Here we've been told this is one-to-one, so we're good to go. So the steps to finding an inverse of a one-to-one function is first think about the function, and then interchange the x and the y. Interchange literally means where there was an x, write a y, where there was a y, write an x. And now solve this equation for y. So to solve this, I'm going to cross multiply the y plus 4 to the left side. Distribute the x. We get xy plus 4x is equal to 3y minus 1. I'm solving for y, so any term with a y needs to come to the left. So xy stays on the left. The 3y moves from the right side to the left side. Any term without a y needs to go to the right side. So the 4x is going to go over as -4x, and the minus 1 is still there. To solve for y, I want to factor out the y. That's going to leave me with leaves me with x minus 3 times y. It's equal to -4x minus 1. And then divide by x minus 3. So it's -4x minus 1 over x minus 3. And then we rewrite that with the inverse notation. So f inverse of x is equal to -4x minus 1 over x minus 3. And if you're asked about the domain, you know that in the domain x cannot be equal to 3. Let's take a look at example number 9. The function f of x is equal to the square root of x minus 1 is a one-to-one function. Find its inverse. So we do the same stuff. So y is equal to the square root of x minus 2. Interchange the x and the y. So we get x is equal to the square root of y minus 2. Square both sides. We get x squared is equal to y minus 2. And then solve this equation for y. So y is equal to x squared plus 2. And you may think that that's the inverse, but it's not. And there's a problem. So what's the problem here? The problem is the following. When you take the inverse of a function, you have to have a one-to-one function to start with, and you have to end up with a one-to-one function. We started with the square root of x minus 2, which looks like this. It's the square root function shifted 2 units to the right. That's one-to-one. That's no problem. The function we ended up with, though, is the full parabola. And here you can see that the parabola is not one-to-one. Here are 2 points on the parabola that have the same y value but different x values. It fails the horizontal line test. So this parabola can't be the function that we want. So let me get rid of that. And what do we need to do here? Well, we need to think about the reflection property. So let me draw the line y equals x. And now notice that I need the part of the parabola that contains the point that is the reflected point of 2, 0. So that's got to be 0, 2. Okay, no problem there. But then I need the point where this piece of the graph is reflected over y equals 0, which would be the right half. And you can look at some points here too if you want to. So maybe if I look at 6, 2, then at 2 on this graph, it needs to be 2, 6, right? So basically you're looking for the reflection. And you can look at the positives and negatives and stuff and discount this left side here. So now how do we write that? So that's what we got to figure out. How can I describe this as this right side of the parabola only and not the left side? And that is called restricting the domain. So we still have the same expression, but what we tack on now, so we're going to say f inverse of x is equal to x squared plus 2 on, and we have to tell it what domain we want. The domain is the x's, and we want from 0 to infinity. In other words, we only want to use positive x's to create this semi-parabola right here. So that is the proper inverse of that function.